If you saw two animal species that were 90% alike, you would assume they were closely related, right? But what if I told you that they are not related at all? You may have heard the saying that work smarter, not harder. It seems that no one supports this philosophy more strongly than Mother Nature herself. Evolution, like a skilled engineer, is constantly searching for optimal solutions to life's challenges. When a design proves effective, it is often reused, sometimes in lineages that are completely unrelated and separated by millions of years. This remarkable phenomenon is known as convergent evolution. Put simply, convergent evolution is when species that are not closely related independently evolve similar traits, usually because they face similar environmental pressures or lifestyles. This is the biological version of the saying, "If it isn't broken, don't fix it." In today's video, we will explore some of the most astonishing stories of evolutionary twins in Earth's history. From creatures beneath the deep ocean to rulers of the land, get ready to witness how nature has recycled its most successful ideas to create nearly perfect replicas. When we think about evolution, most of us picture a tree of life, where species branch off from a common ancestor and grow more different over time. This perspective is not wrong, but it only tells half the story. The other half is mentioned far less often, yet is no less astonishing: convergent evolution. Convergent evolution occurs when organisms that are not closely related develop very similar physical traits, functions, or lifestyles simply because they face similar environmental pressures. In other words, when nature poses the same survival problem, even species with different starting points tend to arrive at similar solutions. Imagine several engineers in different countries with no contact between them, all needing to build a vehicle that is fast, stable, and energy efficient. Very likely they would all think of the wheel, not because they copied one another's ideas, but because the wheel is the optimal solution to that problem. Nature works the same way. Evolution has no creative consciousness, no plan, and no concern for beauty or uniqueness. It is simply a process of selection. Traits that help organisms survive and reproduce are the ones that persist. The core principle of convergent evolution lies in natural selection pressure. Habitats, such as oceans, skies, deserts, or forests, impose very specific demands. To survive in the ocean, organisms must move efficiently through water, reduce drag, and conserve energy. To fly, a body must be light and capable of generating lift. To become a top predator, sharp teeth, keen senses, and effective hunting strategies are essential. These requirements do not care which group an organism belongs to or who its ancestors were. They simply select individuals that meet these harsh conditions. That is why convergent evolution shows us that nature does not have unlimited options. Life is incredibly diverse, but effective designs are relatively limited. A streamlined, torpedo-like body is ideal for fast swimming. Wings are an almost unavoidable solution for conquering the sky. Forward-facing eyes improve depth perception when hunting prey. When different species are pushed into similar circumstances, they gradually and accidentally begin to resemble one another, even though genetically they may be separated by tens or even hundreds of millions of years of evolution. It is important to emphasize that similarity in convergent evolution does not come from a recent common ancestor, but from shared environmental pressures. This is what makes the phenomenon so distinctive and sometimes confusing. At first glance, we may easily assume these species are closely related, but when we examine their anatomy, genetics, and evolutionary history, the truth is entirely different. One of the most classic and striking examples of convergent evolution lies deep beneath the ocean, where hundreds of millions of years ago, nature created creatures so familiar in appearance that modern humans are often fooled. Ichthyosaurs, prehistoric marine reptiles, are often seen as the ancient counterparts of modern dolphins. At first glance, the resemblance is astonishing. Streamlined bodies, prominent dorsal fins, elongated snouts, and powerful tails built for speed in water. But the truth is that ichthyosaurs are not closely related to dolphins at all. One is a reptile, the other a mammal, and both descended from ancestors that once lived on land. This similarity is no coincidence. The ocean is a high-drag environment, where any creature that wants to move quickly and hunt efficiently must answer the same question. How can you swim fast without wasting too much energy? Time and again, evolution has arrived at the same answer. A streamlined body that reduces resistance paired with fins and tails optimized for propulsion. Ichthyosaurs found this solution more than 200 million years ago, long before dolphins existed. When dolphins returned to the ocean after millions of years evolving on land, nature once again chose the same old solution. A similar story unfolds with phytosaurs and crocodiles. Phytosaurs were semi-aquatic reptiles that lived during the Triassic period, and they looked almost identical to modern crocodiles. Long bodies, short legs, elongated jaws filled with sharp teeth, and eyes and nostrils positioned high on the head. Perfect for ambush hunting beneath the water's surface. For many decades of early research, quite a few scientists believed phytosaurs were the direct ancestors of crocodiles. But fossil evidence and detailed anatomical analysis later revealed the opposite. These two groups were merely evolutionary neighbors, not ancestors and descendants. What is fascinating is that rivers, lakes, and swamps shaped both animals in exactly the same way to become an effective ambush predator in murky water, keeping most of the body submerged while exposing only the eyes and nostrils provides a massive survival advantage. As a result, despite their different evolutionary histories, phytosaurs and crocodiles ended up with silhouettes that are nearly indistinguishable at a glance. This is a textbook example showing that convergent evolution does not just copy appearance, but also repeats hunting strategies. The story becomes even more surprising when we look at the imaginary relatives between whales and crocodiles. Ambulocetus, one of the earliest primitive whales, lived a semi-aquatic lifestyle, with a long body, strong limbs, and sharp teeth, resembling a crocodile, with fur. Although it is classified as a mammal and is an ancestor of modern whales, the way it moved and hunted in water strongly recalls crocodilian behavior. This similarity highlights an important point. When animals return from land to water, evolution often reuses strategies that have already proven effective. Ambush attacks, sudden strikes from below the surface, and the use of powerful jaws to seize prey are strategies that appeared very early in the history of life. Ambulocetus and crocodiles, despite being genetically distant, occupied very similar ecological roles, and as a result, their body forms converged. One of the strangest and lesser-known examples is Stomatosuchus, a giant prehistoric crocodile with an entirely unusual jaw structure. Unlike typical meat-eating crocodiles, Stomatosuchus is thought to have had a broad, weak jaw that may have been used for filter feeding, similar to how modern baleen whales strain plankton from seawater. Although fossil evidence remains limited, this hypothesis has opened up a new perspective. Even feeding strategies that seem highly specialized, such as filter feeding, can evolve independently in completely unrelated animal groups. If this hypothesis is correct, it offers strong evidence that evolution does not hesitate to repeat effective ideas even in groups we would least expect. A filter-feeding crocodile and a filter-feeding whale, separated by tens of millions of years of evolution, yet both solving the same problem: how to exploit small, abundant food sources in water. Convergent evolution is also clearly visible in animals with protective shells. Placodonts, a group of Triassic marine reptiles, had flattened bodies, hard shells, and powerful jaws for crushing shelled prey, making them look remarkably similar to modern sea turtles. However, placodonts were not turtles, and turtles did not evolve from placodonts. The two groups simply arrived at the same solution: hard shells that provide protection from predators while allowing access to food sources few competitors can exploit. Finally, we can mention renonids, an ancient group of fish with flattened bodies resembling modern rays or flounders, living close to the seafloor, burying themselves in sand to avoid predators and ambush prey. has repeatedly driven evolution toward the same body shape: flat, wide, and pressed against the seabed. Despite being separated by hundreds of millions of years, these fish still look familiar to modern eyes, as if nature had stored a ready-made blueprint for life on the ocean floor. Oceans, swamps, and seafloors are not just habitats, but harsh problem sets that force life to continually search for optimal solutions. And when a solution proves good enough, nature is willing to use it once again. When we think of armored creatures, we often imagine a distant prehistoric world, where armored dinosaurs like Ankylosaurus roamed Cretaceous forests, covered in dense armor and wielding tails like iron clubs. But if we look at the modern world, we find much smaller creatures, such as armadillos. Despite vast differences in size, era, and evolutionary lineage, both share the same core survival strategy: passive defense through hard armor. In environments where predators are always lurking, running faster is not always a viable option. For slow, heavy animals, evolution has repeatedly chosen the same solution: turning the body into a mobile fortress. In armored dinosaurs, bony armor developed from the skin combined with spikes and bony knobs. In armadillos, the armor is formed from small bony plates embedded in the skin. Two different evolutionary paths converging on the same goal: survival by discouraging attack. Convergence becomes even clearer when we look at Prehistoric, a massive herbivorous animal that lived before the dinosaurs, and compare it with modern elephants. Prehistoric is not related to elephants, but if we look only at its overall shape, a bulky body, pillar-like legs, and a large head, it is easy to think of the largest land animal alive today. Both evolved to occupy the same ecological role: large-bodied herbivores with few natural predators once fully grown. When size becomes an advantage, evolution is often accompanied by similar changes: strong bones to support great weight, digestive systems adapted to processing large amounts of plant matter, and a slow but enduring lifestyle. Prehistoric discovered this formula hundreds of millions of years ago. And elephants, despite appearing much later, arrived at the very same solution once again. This shows that in certain ecological roles, large size is almost an unavoidable path. Another equally familiar image is the similarity between horned dinosaurs and rhinoceroses. Species such as Triceratops possessed massive horns, enormous skulls, and flared neck shields like living armor. Modern rhinoceroses, although mammals, carry keratin horns and heavily built bodies with remarkably similar defensive strategies. In both cases, horns are not only weapons, but also visual signals, clear warnings to predators that any attack will come at a high cost. Here, convergent evolution is found not only in form, but also in social and ecological function. Horns are used for self-defense, territorial disputes, and sometimes to display strength to members of the same species. When environmental pressures force large herbivores to defend themselves against formidable predators, evolution once again nods toward the same idea: weapons permanently attached to the body. Convergent evolution does not always produce giant creatures. Pacharucos, a small hoofed animal that lived in ancient South America, looks surprisingly similar to modern rabbits. Long hind legs, a compact body, and powerful jumping ability, all serving a single purpose: escape. Although Pacharucos was not a rabbit and had no close evolutionary relationship to one, in open environments where predators hold the advantage in speed, a strategy of run and jump proves extremely effective. This convergence shows that even at small scales, evolution is constrained by similar physical limits. A lightweight body, long legs, and fast reflexes form an almost optimal toolkit for small herbivores living on open plains. When the survival problem is the same, the solution evolution arrives, it becomes familiar. One of the most famous and deeply regrettable examples of convergent evolution is the thylacine, also known as the Tasmanian tiger, and the wolf. The thylacine was a marsupial, while the wolf is a placental mammal. Yet their overall appearances were astonishingly similar. Long snouts, sharp teeth, and the lean build of pack-hunting predators. These two species lived in different parts of the world, but each occupied the role of an apex predator within its ecosystem. This resemblance once led many people to believe that the thylacine was a marsupial wolf. In reality, this was simply the result of convergent evolution. When hunting efficiently on land is required, traits such as powerful jaws, sharp teeth, keen senses, and endurance running are almost mandatory. The thylacine arrived at this solution independently, before human interference drove it to extinction. A tragic reminder that evolution does not always triumph over history. Finally, we can look up into the treetops to see convergent evolution in behavior and lifestyle. Suminia, an ancient herbivorous reptile, is believed to be one of the earliest animals to adapt to life in the trees. Its limb structure, gripping ability, and agile movement strongly resemble those of monkeys, the master climbers of the modern animal world. Despite being completely unrelated, both demonstrate that when life moves upward into the canopy, evolution favors traits that enable grasping, clinging, and three-dimensional movement. Suminia and monkeys remind us that convergent evolution is not only a story of outward appearance, but also of lifestyle. When a new ecological space opens up, such as the forest canopy, organisms flexible enough to exploit it gradually acquire similar traits, regardless of their origins. From armored dinosaurs and giant herbivores to land predators and tree-dwelling climbers, all of them point to the same conclusion. Evolution does not create without limits. It is guided by the environment, by physics, and by specific ecological roles. And when those conditions repeat, nature does not hesitate to repeat itself. In evolution, it is not only body shape that can converge. Sometimes invisible abilities, such as how organisms perceive the world, navigate space, or obtain food, are also invented multiple times by nature in completely unrelated species. The following two examples show that convergent evolution goes beyond appearance and extends into how organisms see, hear, and interact with the world around them. Bats flying through the darkness, whales diving deep into the vast ocean where light is nearly absent. At first glance, these two groups of animals seem to have nothing in common. One consists of small, winged mammals living on land and in the air. The other includes massive, legless creatures living entirely underwater. Yet both share one of the strangest and most sophisticated biological abilities ever to evolve: echolocation. Echolocation operates on a seemingly simple principle: emitting sound, listening for the echoes, and using changes in timing and frequency to draw a map of the surrounding space. But to achieve this with high precision, an organism requires an extraordinarily complex biological system. Specialized sound-producing organs, ears, and brains capable of processing acoustic signals with delays measured in thousandths of a second. In bats, this ability allows them to fly through complete darkness, avoid obstacles, chase tiny flying insects, and even distinguish whether prey is moving or still. In toothed whales, especially dolphins, echolocation enables hunting in murky water, navigation during deep dives, and communication with others across vast distances. What is astonishing is that these two groups did not inherit this ability from a common ancestor. The ancestors of bats were small land-dwelling mammals, while the ancestors of whales were ancient hoofed mammals. Echolocation evolved independently in two separate evolutionary lineages, simply because their environments posed the same problem: how to see when eyes are no longer useful. If long claws often bring to mind fearsome predators, the next three animals force us to think again. Giant pandas, prehistoric giant sloths, and therizinosaur, a bizarre group of dinosaurs, all possess long, curved, and powerful claws. Yet the purposes of these claws are completely different from what we usually imagine. Giant pandas, despite being classified as carnivores, live almost entirely on bamboo. To process such tough, fibrous, and hard-to-digest food, pandas need strong forelimbs and long claws to break, pull, and hold bamboo stalks while feeding. They do not use their claws to hunt prey, but to optimize plant consumption. Giant sloths, massive creatures that once lived in the Americas during the Ice Age, also possessed remarkably long claws. With bodies weighing several tons, they were not agile climbers like modern sloths, but they could stand upright and use their claws to pull down branches and strip leaves from above. Standing upright allowed them to access food sources beyond the reach of many other herbivores, giving them a clear survival advantage. Therizinosaur is perhaps the most puzzling case of all. As a theropod dinosaur, a group usually associated with ferocious predators, Therizinosaur instead had small teeth, weak jaws, and clear signs of a plant-based diet. They possessed claws up to a meter long, leading many to assume they were weapons. However, most evidence suggests these claws were used to pull branches, gather vegetation, and for defense rather than to kill prey. Life on Earth is extraordinarily diverse, but it does not develop at random. Each environment is like a difficult question that nature continually asks. And whether that question is posed in the ocean, on land, or in the sky, in the present or hundreds of millions of years ago, evolution tends to arrive at similar answers. Not because species copy one another, but because certain biological designs have been proven optimal for survival. If you find the natural world more wondrous after this video, if you were surprised to learn that dolphins and ancient marine reptiles once looked alike, or that leaf-eating dinosaurs and pandas could share similar survival strategies, then don't forget to press like to support the video. That helps the channel reach even more people who love science and nature. And if you enjoy stories about evolution, ancient life, the mysteries of existence, and the hidden rules behind the natural world, subscribe and turn on notifications so you won't miss future journeys. There are many more stories out there. Stories that show that no matter how diverse life becomes, nature always returns to the same question: what helps you survive?